The quantum model of the atom can be a difficult model to understand because of the quantity of experimentation that actually went into its development. So where we had previously left off was with the Rutherford model of the atom. It was a very simple model called the cloud model. The cloud model had a positive center nucleus, and around the outside, scattered in not really any certain order, were the electrons. Before we move too much further with how we get into the next model of the atom, there's a couple things that we do need to understand, and that's, first of all, what happens when an electron is exposed to energy. And now this can be an energy in any form, so you're talking about heat, light, electricity. So when an electron is bombarded with energy, it tends to absorb that energy. And when it absorbs that energy, it's going to start to move faster, faster and faster. It can then actually break away from the pull of the nucleus and move further away from the nucleus into something that we call the excited state. Now, the excited state is a temporary, very high energy state, and it can't maintain it for very long. So the exact amount of energy that it absorbs, it then lets go and goes back down to its original position, which we know as the ground state. Now, the weird thing is that when the electron lets go of that energy, it only lets go of it in the form of light. It emits something that we call a photon. The next thing that you need to understand is that the color of light is directly proportional to the energy that it lets go of. So depending on how far it actually moved out in the atom will depend upon the color of light that we see. If it only absorbed a little bit of energy and it only has to let go of a little bit of energy, we're going to see a very low energy light, and it's going to be closer to the red side of the spectrum. If it absorbed a very high amount of energy, it's going to be closer to the blue side of the spectrum. So back to the Rutherford model of the atom. If we would expose the Rutherford model of the atom to energy in any form, and if the Rutherford model of the atom is correct, then any one of those electrons can absorb an amount of energy. Let's just say it's a small amount of energy. That electron is going to be able to move a little bit further away from the nucleus, stay there for a little bit of time, let go of energy, a low amount of energy, so it's going to emit maybe, say, like a red light, and then move back down into its ground state. Well, in like manner, if it absorbs a larger amount of energy, it should be able to move further away from the nucleus, stay there for a little bit of time in its excited state, emit a bluer form of light, and then move back down to the ground state. So theoretically, if Rutherford would have been correct, and we expose an atom, hopefully with the Rutherford atom, to energy, what we should be able to see is those electrons absorbing a variety of different amounts of energy, emitting a photon, and then falling back down to the ground state. But again, if they can absorb any amount of energy, then we should see a variety of different colors of light coming back out of that atom. Effectively, we should either see one of two things: a rainbow of color, or, since all of the forms of light together come together to make white light, perchance we would only ever see white light coming out of an atom. So this is something that we can test, and the test that we normally do is called flame testing. So we'll take an atomic sample, throw it into fire as a form of energy, and just see what happens.
We're going to do a flame test on a number of selected compounds, primarily group 1 and 2 ions. And these are aqueous solutions, and we have just a inert metal loop. We're going to dip the end into the solution and put it into the flame. And that excitation characteristic color is like a fingerprint for an element. So we're going to look at a number, and then we're going to ask you to identify some unknowns. potassium. It should be a lavender. Is it barium? Is it green? This is calcium. Calcium. With a yellow red. Strontium. This one's a pretty red one. Lithium. Sodium is a bright yellow. The last one is copper. This is the most vivid of all of them. It's green.
So what you should notice is that no one atom emitted either a rainbow or white light. Now what that means is that Rutherford's model of the atom is incorrect, and that there must be something else happening with the electrons around the outside. So enter the Bohr model of the atom. Now Bohr decides that the reason that there's only one certain color coming out of the atom is that the electrons must be restricted in their movement on the inside. So he places the electrons in concentric rings around the nucleus, and he says that the electrons can only travel from one ring to the next. That means that there's only one specific amount of energy, or quanta of energy, that can take an electron from one ring to the next. So we really only should see one color of light coming out of any atomic sample. So what I'd like to show you next is what happens when you think about the colors that you're actually seeing. And this actually kind of caught up to us when biology proceeded a little bit further and we learned a little bit more about our silly little eyes.
He's probably one of the science toys, a little white plastic ball. It's not actually one plastic ball at all. You don't bring white plastic ball. It's not totally cool that. I don't call it purple, it's a purple ball. That would be. And, you know, I'm not good with colors, I don't know colors in the future, but it's, you know, this purple. What did you say that? It's line, but it is actually a red, blue, green line. But it looks purple. Because if you really green like that, alright, well, I already said this is big. I can show you that it is red, blue, green. I can do that. But the believe is simple. You're going to twirl it and circle it, and all of a sudden you're going to see red, blue, green. I won't see nothing less. Okay. Pretty good promise. Let's take it. Wow. Okay. So, not too big of a person to admit when I'm wrong, and I see the red, green, and blue balls around the outside of the circle. But when you slow down, it becomes like being purple, and it's not actually everyone will say pink purple because the red, blue, and green lots of tiny little off specifically after each other that your brain actually notices things going on when the wolf reflects. So the eye actually kind of follows the information there about what color the stage brings the moment it's there. And we're just together to produce that purple color. And that red, blue, and green kind of moves to discuss the violet color. That's the vibe. You know your colors. You want can we see those separate when you swirl in a circle? When I swirl in a circle, I'm actually getting them all to switch colors to red, to green, to blue, at different points in space. So at different points in space, your eyes are actually holding an image as it switches to a different color. Right, so even in the eye, I'm remembering seeing color that it's seeing, it's not remembering the next color because that occurs at a different point in space exactly. So it's much easier to see the red, blue, green light happening in the ball than it is when it's still. So we need to think about some practical applications for this.
So what we found out is that our eyes are actually not smart enough to be able to see the individual colors that could potentially be coming out of these atoms. We don't know whether or not we only have one color of light or several colors of light coming out of the atom and then just merging together into one color. So we need a tool to be able to separate out these different forms of light, and the easiest form would be a prism. Now, a prism takes white light and separates it out into its individual components, basically letting us see the rainbow of color that white light is made up of. So the next experiment that was done, just to try and see if Bohr's model of the atom was correct, was to take samples of atoms and expose them to different forms of energy. In this particular experiment, we're taking hydrogen and exposing it to electricity, and we see that it emits photons, it glows. But this time, instead of just looking at it with the naked eye, we take that light and send it through a prism, and we take a look and see what actually emerges on the other side, and to everybody's surprise, we actually see several colors coming together, although our eyes only see one. Now this basically disproves the Bohr model of the atom, because we are seeing more than one color. His model of the atom doesn't allow for all of these different colors to be seen. So now we know that there must be something else going on inside of the atom, and unfortunately, it takes many different scientists to try and come up with the newest, latest, greatest form of the atom called the quantum model of the atom.